它可以自己把数据看声音看看。就我现在设置的是不能自己放这个。哦。我们是2个小时吧，然后我们应该还有。So again, so the online friends, can you hear us clearly? 你看一下他那个，他有没有人回信 ？Yeah, yeah. Can you hear the sound clearly? Yeah. Yes. Okay, good, good. Thank you. Yes. Yeah. Let's start. Yeah.
Okay.
So let's continue with our study group. So yesterday we learned from Professor Sachdev this overall picture of his series talks, and we started with the spin liquid constructions. So today I think we will continue from there, and we will go to the more ambitious phase diagram of the cuprate, right?
Yes.
So today we have 2 hours lectures, maybe 1 break, and let's welcome Professor Sachdev. Yeah.
Okay, yes, so I'll try to do in 2 hours what really has been a vision going back to the very earliest date of cuprates in 1987, starting with Phil Anderson, of how you connect spin liquids to superconductivity. This idea has, people were enthusiastic for a while, then it faded away, but I think it's now coming back. And I'm going to give you some recent ideas, which I'm pretty excited about, on the connection between high temperature superconductivity and spin liquids. Anyway, but to go back to where we were, we did the Schwinger boson theory of some antiferromagnet. And then I discussed the general structure of a theory on a non-bipartite lattice, like the triangular lattice. And we showed that ultimately when you looked at the full structure of fluctuations about the saddle point, you ended up with the Z2 spin liquid, which has the same topological order as the toric code. All right, so this is, of interest and perhaps connected to recent experiments on Rydberg atoms, where they actually make artificial Kagome lattices and Ruby lattices. And it could well be that such a system is realized there. But for the cuprates, this seems rather unlikely. There's never been any chance of any sign of some gap spin liquid like this. Even for square lattice antiferromagnets with, say, if with first and second neighbor exchange interactions, you go into some possible spin liquid state only when the second neighbor interaction is 1/2, J2 is 0.5 times J1, whereas in the real system, J2 is 0.1 times J1 or even smaller. So this doesn't seem to be of much relevance to the cuprates, although there has been a lot of work on doping Z2 spin liquids, but I won't talk about that. I want to go back now to the square lattice, where we had a rather different structure. And in fact, we just had a discussion of the honeycomb lattice yes, there you are. Sorry, I forgot your name. Where also has a common feature that the honeycomb lattice is bipartite. And as a consequence, there's a U1 gauge symmetry left over. So instead of getting a Z2 gauge theory, you get a U1 gauge theory. So today I want to say much more about the structure of this U1 gauge theory. So for beginning first with the insulator. So on the square lattice, you have a U1 gauge invariance where the Schwinger boson on one sublattice has, say, positive charge. And the Schwinger boson on the other sublattice, A and B sublattices, has the opposite charge. Okay. So you can do a mean field theory where you get some spectrum where, as a function of K, there's some minimum this is omega of the Schwinger boson, some dispersion. And you can try to then write down some effective theory for this minimum. Okay, so I won't go through all the steps. I mean, I'm going to get to some, and I'm not going to really use this theory. So let me just roughly outline what happens. So you have these bosons that are sitting near the minimum, and you try to now look at the minimum, the low energy theory where this gap is becoming small. Okay. So what happens is that you have this boson here, and there's, in the low energy theory, it can be expressed in terms of some combinations which called Z alpha, which is roughly just a linear combination of this. So it's the B on one sublattice plus B dagger on the other sublattice, where alpha is a spin index up and down. So this has a U1 gate charge. And so that the low energy theory of this boson gives you a Lagrangian, which turns out to be relativistic. And so you get this following Lagrangian. This is both space and time derivatives, minus I A mu. There's a U1 gauge field. And then you will get some potential, some mass term, plus U Z alpha to the fourth. So this is, sorry. This, if you wish, is what you get as the low energy theory of the Schwinger boson theory on the square lattice, or really on any bipartite lattice at low energy. So there's a U1 gauge field, and there's a complex relativistic boson, which which is moving with the gauge field interaction. Okay, so this is sometimes called the CP1 model for obscure reasons, but this is what this theory is. Okay. So we want to now study this theory a little bit to see what it tells us about the square lattice low energy theory. Okay. All right. Okay. We need some. It's not erasing very well. Okay. Oops. All right, so we imagine we have some square lattice antiferromagnet, and these are some parameters that depend on the microscopic couplings in a way that we don't fully know, but we want to just say something about the general structure, the phase structure of this theory. Okay, there's an emergent U1 gauge field, which we discussed how that appears last time, and then it's coupled to this relativistic scalar. Oh yes, what I was going to say, why is it relativistic? It's relativistic roughly because of the spin inversion symmetry. S goes to minus S in an antiferromagnet is good. And so when you take the two sublattices into account, there is no, you get a theory which is relativistic, and this has the ability to get you linearly dispersing spin waves. And we know in an antiferromagnet, spin waves have a linear dispersion, which has also a relativistic structure. But of course, you can derive this microscopically from the saddle point and carefully looking at the low energy limit. All right, so now you can ask, as a function of this coupling S, what is the phase diagram? So when S is negative, you can imagine two phases. If you just do some mean field theory, there's a phase where Z alpha is condensed, and there's another phase where Z alpha is not condensed or gapped. Now, this being a gauge theory, you will say that there's this is what you call a Higgs phase. And that's, we'll have to worry about what that phase is in a minute. But let's try to understand this Higgs phase, which is a bit easier to understand. So now maybe you've seen, learned a little bit about the theory of weak interactions, where you also have a Higgs field. And what the Higgs field does there is completely gap out, gives you a mass to the gauge boson. So it means the gauge fields are no longer mediate any long range interactions. And that's what happens here too. The Higgs field gaps out this A mu, and so you don't have to worry about the gauge field. It is some massive mode. All right, so the gauge boson is gone. You're in some comfortable state of matter, which doesn't have any emergent gauge field. So that's good. But now, unlike the theory of weak interaction, this Higgs boson also breaks the symmetry. And the reason it breaks the symmetry is because I can write down a composite operator. If I look at this operator, Z alpha star, sigma alpha beta, Z beta, this is gauge invariant. If I do the gauge transformation of Z, this is gauge invariant. But this also is a vector. And so when Z condenses, this vector will take, depending on the orientation of Z, this will take a definite value. So this is also not equal to 0. And a non-zero value of this object breaks the symmetry. This by itself doesn't break a symmetry because this is a gauge-dependent object. But this is a gauge-invariant object, so you break a symmetry. And what is this object? Well, again, you have to go back to the microscopic derivation and look carefully at what this object is, and it's precisely the Néel or antiferromagnetic order parameter. So this is just this phase that has antiferromagnetic order. Well, this is a very complicated way to get what we already knew was a ground state of the square lattice antiferromagnet. It's the classical Néel state with spins polarized in opposite directions on the two sublattices. All right, so that's the easy part. How about the other part? Okay, so this is where quite a bit of analysis is required to understand what the other phase is. I could spend the rest of the 2 hours describing it. There is in the book that is about to come out, there is, slowly you're led through exactly how it's all done, but let me just outline what happens. So first of all, if we begin naively, you say, well, Z alpha is 0, so it's gapped out. So there is no Higgs phase. So when you gap it out, you forget the Z's. And so here you would say that the effective theory, you can imagine integrating out the Z's. The only thing left over is mu. So the effective theory will be just some Lagrangian, or Lagrange effective would be basically F mu nu squared, where F mu nu is d mu a nu minus d mu a mu. So it's 2 + 1 dimensional electrodynamics. So you have a photon. Okay, so this photon is going to mediate an Coulomb interactions. Now these are massive particles. They have 2 opposite charges. Opposite charges will attract, and so there will be a very strong attractive interaction between the Z alpha. But that's the Coulomb description. However, what's known, but that's not the whole story. This is because this theory is sitting on a lattice, and this is a bit misleading. If you go back to the lattice derivation, you realize that it's not just ordinary quantum electrodynamics, it's what's called compact quantum electrodynamics. This means that you're putting everything on a lattice, and on the lattice, as the Z are moving around, as the Z hops from here to here, they pick up a phase factor, which is e to the IA, as Z goes from here to there. So really, the lattice version of this theory is Z alpha star at site I, e to the I aij, Z alpha j. So, and in the long wavelength limit, this gives you this. Okay, but this theory has a very special property which this does not have, and this is actually the actual theory. This theory has a property that aij goes to aij plus 2 pi. It doesn't change anything. It's periodic in A. Okay. Now, is that important? Well, depends. So if you take the XY model, is the periodicity important? Well, if you're in 3 dimensions, if you take a classical XY model, which is described by phase theta, then in 3 dimensions, the low energy theory is just grad theta squared, and that describes the long range ordered phase of the XY model. But in 2 dimensions, we know that we have to worry about vortices, and the vortices can proliferate and describe the costless Thouless transition. from the superfluid phase to the normal phase at finite temperature. So here, a similar thing you have to worry about. So the actual low energy theory is not F mu nu squared, but if you write it on a lattice, it's something like minus cosine of F mu nu, where F mu nu now is the flux through a plaquette. Okay, so you really have to study this theory to understand what's going on here. Now, fortunately, this theory was studied a long time ago by Polyakov. He studied the 2+1 dimensional quantum compact electrodynamics, as it's called. And what he realized that this theory had monopole. These are not excitation, these were tunneling events. They were where the flux in some region of space changes by 2 pi through a monopole like tunneling events. And this is very much the analog of vortices in the 2D XY model. So the vortices, but now this is a gauge field in 3 dimensions, 2+1 space-time dimensions, and that allows these monopole configurations. So these monopoles play a very important role in many discussions of U1 spin liquids. All right, so what Polyakov showed was that actually no matter how large the coupling here, there's a coupling here, 1 over G, no matter how small G is, these monopoles always proliferate. So in a 2D XY model, if you heard about the costless-Thouless transition, you know that temperature has to be bigger than the costless-Thouless temperature before the vortices appear. So there's a region where the superfluid state is stable. Now, the analog of the superfluid state here would be the free photon phase, where you have long-range interaction from the photon, which are Coulomb-like. But what Polyakov showed was that there is no free photon phase. No matter how small G is, these monopoles eventually always come in. So there's no screening of monopoles, there's no bound phase of monopoles. The monopoles always form a plasma. So it's always like the high temperature phase of the 2D XY model. So that's a long story. But anyway, the net result is that monopoles proliferate, as shown by Polyakov. And this tells us that there's confinement. Confinement means effectively that you're back to some safe ground and there's no photon, there's no emergent gauge field, there's no fractionalization. It's some trivial phase, okay. All right, so you've got a trivial phase and so you can be happy, but there's a problem. So trivial phase meaning all excitations are unfractionalized. There's in fact a gap. There is nothing. Z is gapped. The photon is gapped. It's like QCD, which is always just pure QCD, just a confining phase with only gauge neutral excitations. The only trouble here is that there's a theorem. I mean, now it's didn't exist at the time we discovered this effect. But there's now we can say there's a theorem, sometimes called the Hastings-Oshikawa-Liebschultz-Mattis theorem, that a square lattice antiferromagnet cannot have a trivial ground state for spin a half. If you take the spin or any half integer spin, the square lattice antiferromagnet is forbidden from having a trivial ground state, which means that it cannot have a state which is just a state with a gap to all excitations, which breaks no symmetry. And has only integer spin excitation. That's not possible in the square lattice antiferromagnet. So something must go wrong with this reasoning. Okay. So what's wrong? And there is, lies again another long story. What Nick Reed and I showed in the early 90s. What's wrong here is that these monopoles come with phase factors. They come with additional phase factors. Today, I suppose you'll call them, I don't know, these are Berry phases that are associated with these tunneling events. And when you include the Berry phases, then you find that this phase here, let me use another color. So these monopoles have Berry phases. And when you figure out what the Berry phases imply, these imply that this trivial phase is not trivial. It's what we call a valence bond solid. So this means that here in the valence bond solid, if here's your square lattice, there's a broken symmetry where, say, the spins form singlets in some columnar pattern. And that's what the state is. So on this side, we had the nail state. So here we had this broken symmetry. So in the Higgs phase, you have the nail state. In the confining phase, there's another broken symmetry, and that's really required by the Hastings-Oshikawa theorem. And what the analysis shows that the broken symmetry here is broken translational symmetry. Okay, so that's the conclusion of this analysis, that there are two phases of square lattice antiferromagnets when you describe them with U1 gauge theory. They both ultimately are conventional phases. They both have distinct broken symmetries. All right, so then there's the issue of the transition between them. What is this transition? And that's the whole game of deconfined criticality. Could this be a second order transition? Again, there's a very long saga there. So still ongoing to some extent. But I think now the consensus is no, it's at least for this model, there's no second order transition and it's a first order transition or something. So ultimately then, this square lattice antiferromagnet is in one of these two phases. Okay, and that's numerically, that's very much consistent with numerics. On say the first and second neighbor square lattice antiferromagnet, there are clear signs of this phase, there are clear signs of this phase. What's going on in between? Well, depends on whose work you're looking at. There's still a lot of uncertainties, but the two phases definitely are there. Yes.
So for the valence bound state,
yeah,
able inside the rectangle.
Yes, yeah. I mean, so what I mean by saying so this is not a totally trivial phase. It has a broken symmetry, but it's not a fractionalized phase. In the sense, there are no integers, half integer spin excitations. So here, what happens if you break a bond and you have a spin a half here, well, then these things can move over, and there may be a spin a half here. But now what you see is that this spin a half, if you draw the full lattice, you'll see how that works. So you've just broken a bond and you're trying to move two spin a halves apart. What you see is that this line here has a certain tension. It costs energy. It costs energy because it's not aligned with the broken symmetry. So there's some cost per unit length of this line. And these two spin a halves cannot escape from each other. They're bound to each other. They're confined. So that's why it's not and that confinement is very much driven by these monopoles. Okay. Yeah.
Going back to the contact audience.
Yes.
And their monopole also carry Berry phase.
No, so the monopole really, the Berry phase, just looking at this theory, that's not, it's not there. So you really have to go back to the microscopic spins. You have to have a model with spin a half. It's very much, the Berry phase depends on whether you have a spin a half antiferromagnet or a spin one antiferromagnet. They're different for spin a half. So the UV description does matter. So today there's more sophisticated way of seeing this, saying this in terms of anomalies and various topological terms, I mean, but it's a different way of saying what I just said in the end. Yes.
Probably true question. So originally we had the FMU.
Yes. Yes.
That low energy factor was okay, and then you said that the full theory would be invariant under AIJ conflated by 2 pi.
Yes.
And that will give us the so maybe I missed something. How does FMU transform when AIJ is moved by 2 pi?
FMU goes to FMU plus 2 pi. It's just the sum of A around a plaquette. Yeah. Then if you take this theory and you analyze it just like, so there's a way of analyzing the XY model, 2D XY model, which is cosine theta I minus theta j, using the Villand transformation and doing all kinds of dualities. You do exactly that for this theory, you will get Polyakov result. Yeah. No, no, there's no broken time reversal at all. This is not Chern-Simons. Yeah, I mean, that will lead to a different spin liquid. That will lead to a chiral spin liquid or something. Yeah. But to get the Chern-Simons theory, you should really start with the fermionic spin-ons. Then the band, then there's a fill Fermi band, and if the band has very curvature, you can get the Chern-Simons term. But the bosons, you don't get that. Okay. All right. So that's what I want you to remember. And in fact, this is kind of what I've reviewed here. So let me put that up. What's going on? Okay. Okay, this is work with students Main and Henry and postdoc Jude Chilio, former postdoc Matthias Schurer. Yeah, and well, I won't talk about work with them. Okay, so this is what I have just summarized for you. That the bosonic Schwinger boson representation gives you these two phases. Okay, and let me X that out. Oops, what did I do? Okay, I don't know. All right, so now let's go back and let's do Schwinger fermions. So let's go to the square lattice and let's do it using Schwinger fermions. And so, the whole steps are exactly the same.
Oh, okay, that's fast. Okay.
Okay. So if you do it using Schwinger fermions, then you get J times SI dot SJ again. And now SI is 1/2 F dagger I alpha sigma. And then, you have the constraint on each side. Okay. Now, at first glance, it seems like you don't have, the procedure should be very similar. And there's some U1 gauge theory. And you look for a saddle point with a U1 gauge invariance and work with it. So that's, in fact, there's been a lot of work on such a U1 gauge theory saddle point. It's called the staggered flux phase. So that has gapless, unlike the bosonic case where you had gap bosons, this has gapless Dirac fermion in this low energy spectrum. And then you have to figure out monopoles. The monopoles are still possibilities here. And that's taken a lot of work. And so for the staggered flakes, the monopoles were first studied by Jason Alessia, and more recently, Tong Wang and Ashwin Vishwanath and various people have studied it and yes, confirmed some of Jason's result and also understood them in a more broader context. And what they find is that in this theory, the staggered flux phase, and there is a trivial monopole, meaning that there's a monopole which has no buried phases. Now that's bad news because this means that you're running into the same contradiction I mentioned, that this monopole will proliferate very easily. And it will confine the theory, but there's no obvious confining phase. So the problem is just probably flows to something else. All right, so that might be, enough motivation to give up on this approach. But there's another way to do this, which sidesteps the whole issue of monopoles, which is the recognition, which again goes back to a very early work of Affleck et al., that this theory, in fact, in principle, could have not just a U1 gauge invariance, but an SU2 gauge invariance. Okay, so that's quite remarkable, but let me just point out roughly how that happens. So naively, you would think that if there's a local constraint like this, that you have just a U1, there's one constraint, and so there's a U1 gauge symmetry associated with it. But in fact, there's another way to say this. So let me rewrite this in a different way. So I'm going to introduce the capital F, which is going to be a matrix. And this is where I need to look up my, oh, it's in there. Okay, if I want to get all the signs right, I have to look it up. And I probably need my glasses also. Okay, so I invite you to check the following, that if I define this matrix F, it's on every side, so let me just not put all the sites everywhere, which will be F up, F down. And then this would be minus F dagger down, F dagger up. Okay, so I just defined this matrix. And then I can rewrite the spin operator in terms of this capital F, the same spin operator is equal to 1/4 trace of F dagger sigma F. Okay, so you just insert this in there and go through and work it out, you'll get the same expression, okay? All right, so but now this expression exposes something very interesting. What this shows you is that first of all, there's two different transformations I can make. I can take F and multiply by unitary matrix on the left, or I can take F and multiply by unitary matrix on the right. These two are different operations, different unitary operations. In fact, you can go back and check they're completely consistent with each other because you know, this thing appears twice. So if you do unitary transformation, you want to make sure that this and this transform in a consistent way. And you can check that it does work that way. And then these two are independent operations. So there's really an SU2 cross SU2 transformation you can make on these Fs and go to a different basis. Okay, so what are these transformations? Well, if you look at this expression here, one thing you notice is that if you do this transformation, S goes to S. The spin is invariant under the right because the V will go here and a V dagger here, and you trace it over, you get back to S. Whereas over this way, and this one is not, S will go to some rotation matrix times S. And you can work out what that is. So this is really an SO3 rotation. So what you see that the left multiplication is just spin rotation. It's the usual global spin rotation symmetry, but right multiplication is a gauge symmetry. You can do F different on different sites. So just like the U1 gauge symmetry, so this is an SU2 gauge symmetry. SU2 gauge, and this is SU2 spin. Okay, so in fact, this Schwinger fermion representation, unlike the Schwinger boson representation, has not just a U1 gauge symmetry, it has an SU2 gauge symmetry. Okay, so for the rest of my talk today, I'm going to talk much more about this SU2 gauge symmetry. So this is also recognized in the very early days of ITC, but for mysterious reasons, really wasn't studied as carefully as it should have been, I believe, as I hope to convince you today. Okay. So now we're going to try to, insert this in here and look for some saddle point. And we want to look for a saddle point where this SU2 gauge symmetry is unbroken. Then we'll have an SU2 gauge field to worry about. Well, SU2 gauge field might seem like more complicated than U1 gauge field, but fortunately an SU2 gauge field has no monopoles. So you don't have to worry about monopoles, but you do have to do the full SU2 gauge fluctuations. So that's what you benefit. All right, so let me just then show you how that proceeds. Right, so you take the square lattice antiferromagnet, you write it in terms of these fermions, and then, well, yeah, oops, yeah, it's over here. I'll come back to that. And you look for a saddle point. So I'm going to imagine I get this saddle point, which is called the pi flux saddle point. This is the yeah. Okay. So what is this? So the EIJ is just a constant. It's -1 on the green links and +1 on the red links. So notice this has pi flux around every plaquette. But I'm going to put a factor of I for reasons that'll become apparent in a minute. If I put the factor of I here, then you know, going from I to J has the opposite sign from going to J to I to make the Hamiltonian invariant. This doesn't break any time reversal symmetry, as you can check by various transformations later. You can undo the time reversal transformation by a gauge transformation, so it doesn't break anything. Okay, so this is a gauge choice for the pi flux phase. The flux is pi, so naturally there's no broken time reversal. But if you write it in terms, so this form of the mean field theory for the Schrödinger fermions is clearly invariant under global SU2. It's invariant under this because it's just a trace over alpha. So it's invariant under this transformation. But now, this is, you can now check. Another thing would be fun to check, just like you can check this, you can check the following. That if I introduce this Nambu spinner, F up, F dagger down, this is equal to this. Okay, in terms of the size, which is this Nambu spinner. Now, if you look at this Nambu spinner psi, and you multiply it on the left by unitary matrix, that transformation is exactly this V. So if you just, this is a slightly different notation, multiplying F by V on the right-hand side is same as multiplying this column vector by a matrix on the left-hand side. It rotates between the particles and holes. You know, to get spin rotation, you have to rotate between F down and F up and F down. But if you rotate between F up and F down dagger, that's a number rotation in particle hole space. Okay, and this thing is clearly invariant under SU2 gauge. Okay, so that's a low energy theory. But now I have to put an SU2 gauge field in there too. So our theory for the square lattice antiferromagnet is going to be the following. So our mean field Hamiltonian in this is going to be minus ij sum on nearest neighbors, eij. Then I have psi dagger I. But now I put a gauge field, which will be uij psi j minus psi dagger j, uji psi I. Okay, and now U is some gauge field sitting on every link, which belongs to SU2. So that's the theory that you get from the Schrödinger fermion representation. This is a highly non-trivial theory. There's fermions hopping on the square lattice with pi flux, and then there's an SU2 gauge field. Okay. Previously, you had a U1 gauge field e to the IA, but now you have a whole matrix that you have to put in and figure out what's going on with this. Okay. So I think today we have a pretty good idea what the phases of this theory are. And the answer is actually very beautiful. The phases of this theory are the same as the theory of the Schrödinger boson. Today, we believe that this theory, if you study it, will give you the nail in the VBS states. exactly the same. So in fact, the two theories give you the same answer, which again is a very satisfying conclusion of the structure of the square lattice antiferromagnet. Okay, so how does that work? Well, first of all, you put Uij equals 1. If you put Uij equals 1, then this psi has, because it's just moving in pi flux, you get 2 Dirac fermions. So it has a dispersion with 2 Dirac fermions in some 2 points in the Brillouin zone. That depends on your gauge choice. And you take the low energy theory and put in fluctuations of this. So in the end, the low energy theory of this thing becomes L is equal to psi bar d slash psi, where the number of Dirac fermions is NF equals 2 for the 2 valleys. And this d slash is just the continuum of the SU2 covariant derivative. So that's the theory then. It's really very simple in the continuum limit. And this is a theory that lattice gauge theories have studied. Here you don't have to add any Berry phase, nothing. This is the full theory. And you can study it and look at some of its symmetries and well, sorry. I should say this theory plus ... You will have to add a few more terms to really get the full structure. Anyway, so what have lattice gauge theories found about this theory? I think this is what I said over here. Yeah, so there's the theory down here. S takes 2 values, the 2 valleys, and psi is just a fundamental of SU2 and a 2-component Dirac fermion, SU2 gauge. Oh, sorry, there should be a gamma maybe here. All right. Okay, so what can you say about this theory? So first of all, this theory could be, it has a scale invariance because there's no mass term or anything. So it could be a conformal field theory. It's what we call possibly a conformal gauge theory, where at low energy, there's some CFT in 2+1 dimensions. And in fact, if you do the large NF theory at large NF, that is correct. You in fact find a gauge theory, conformal gauge theories with some anomalous exponents. And so that will be predicting some very critical spin liquid state, which has gapless excitations, no quasiparticles, some strongly coupled conformal field theory. Okay, that would be an exciting possibility. But for NF equals 2, I think the consensus now is from a lot of work, including Bootstrap, that this conformal gauge theory does not exist. It may exist for large NF, everyone agrees with that. But for NF equals 2, it's confining. Okay. So it's confining. So then becomes the question of what is the confining phase? Okay. So this is actually very similar to QCD. QCD in 3+1 dimensions also has massless quarks to begin with. And that's also confining. And what in QCD happens is something called chiral symmetry breaking. The confining phase, you get a condensate, which is gauge invariant, but will break certain global symmetries. So here you're in 2+1 dimension, not 3+1 dimensions. So you have to understand what are the global symmetries, and so that will be broken. So this theory, what is the global symmetry this theory has? Okay, so this theory has a global symmetry, and that global symmetry is not immediately evident. So first of all, you might think, okay, there's 2 flavors, so you can rotate between them. So there's an SU2 global symmetry in addition to the SU2 gauge field. But it's bigger than that. And what is the global symmetry? Okay, how am I doing on time? I have to take a break at some point. Oh, okay. So what is the global symmetry of this theory? Okay, to get the full structure, what you want to do, so you have NF equals 2 Dirac SU2 fundamentals. Fundamental Dirac fermions. So now if I didn't have the gauge field, for a moment, forget about the gauge field, and then I have 4 Dirac fermions because fundamental of SU2 has 2 components, and this is 4. So there's 4 Dirac fermions, and so that's equivalent to 8 Majorana fermions. So if I just had, 8 Majorana fermions, call them little psi, d psi, if this was my theory, again, d slash psi without the covariant derivative, then this theory would have an SO8 symmetry, because I can rotate the 8 real fermions in an SO8 group. There's 8 of them. However, it's not d slash, it's d slash, because there's a covariant. So the part of the SO8 that rotates in gauge space is not a physical symmetry, but the other parts are. Okay, so what is the symmetry left over? So there's an so in terms of real fermions, I have an SO3 gauge field. So I had an SO8 symmetry here. You have to pull out an SO3, so you're left over with an SO5 global symmetry. So this continuum theory, as written, has an SO5 symmetry. And this symmetry is going to be broken in the confining phase. Okay. But, okay, so that's great. But the original lattice model, this model here, certainly doesn't have an SO5 global symmetry. What is the symmetry of this theory, even after putting the gauge field, which I haven't written here? Well, it has an SO3 or SU2 spin rotation symmetry, and it's got some lattice symmetry. Let's say there's a Z4 lattice rotation symmetry. So the actual symmetry of the theory is just SO3 cross Z4 for lattice rotations, let's say, whereas this theory is a much bigger symmetry. So this SO3 cross Z4 has been enlarged to SO5. And there's got to be this dot, dot, dot. This is where I put in the dot, dot, dot. There's got to be other terms here that can break SO5. But those are presumably irrelevant because they'll involve higher derivatives and 4 fermions and so on. It's quite plausible, certainly for large NF, these terms are not important. All right. So that tells us there's a confining phase. And just like we found for the Schwinger boson, this confining phase will break symmetries. And it'll break this SO5 symmetry. So we have to understand what is this SO5 made up of and what are the possible broken symmetries. So to do this, you have to go back to the original lattice model and study its symmetries very carefully and study how the SO5 appears out of those actual symmetries. And so given that SO5 is broken, you can then ask what is actually broken in the lattice system. All right, so this kind of analysis has been done very carefully by various people. I think it was done by, what's the name, Ying Ran and Xiaogang Wen in one paper, and more recently by Chong Wang and others. And so when you go through that careful symmetry analysis, what you find is what I wrote down over here. Yeah, so there's a pi flux leads to NF equals to Dirac fermions coupled to a gauge field. There's an SO5 global symmetry. And then you ask, what are the possibilities of it being broken? What you find, depending on the dot, dot, dot over here, you either get the Néel state or the VBS state. So very beautifully, the answer is exactly the same answer that we got from the Schwinger boson representation. And this was formalized by a Clayton claim in this paper here that this theory here with the D slash, sorry, forgot the gamma mu, is dual to the CP1 theory I began my discussion. Okay. with a weakly first order transition between them. So this thing is almost a conformal field theory from a lot of numerical work. That's what makes this transition weakly first order. There's in fact, if people study this region, there's been some very nice work showing that in fact in this region, you can actually see the SO5 symmetry in numerical studies. So, even though it's confining and the SO5 symmetry is only exact at a conformal fixed point, nevertheless, numerically, it's pretty good. So this description is not bad. I mean, and in fact, the fermion description is better than the boson description because the SO5 symmetry is completely hidden in the bosonic field theory, but it's quite explicit in the fermionic theory. So this suggests that if you want to understand this point better, starting from fermions may be a better starting point. It hurts me to say that because I spent so much of my life starting with the other approach. But since this is giving the same answer, okay, I'm happy with it too. Okay, maybe this is take a break now, and then we'll talk about. So that's all I want to say about the square lattice insulator. And the remaining hour, I'll talk about moving away from the insulator, which is, of course, the big problem. Okay.
So maybe we can ask a few
questions.
Yeah. We can ask questions now for now. Yeah. Also the online also the online people. Yeah.
One question here.
Yes.
You just mentioned that the conformal graph has already ruled out the case of the F equals 2.
Yeah.
Conformal gauge theory.
Yes. Yes, correct. I mean, so the conformal bootstrap, never makes any explicit reference to the gauge field because they only have access to gauge invariant objects. So really the only information they put in is that is there any conformal field theory which has an SO5 global symmetry which has no relevant operator which is an SO5 singlet or something like that. They just put in very little information like that, and that already is enough to restrict the set of conformal field theories.
So what I want to use is that what does this tell us about this transition point?
Well, so one possibility, which I think many people are hoping for, was that if the conformal gauge theory existed, then this would be a deconfined critical point. And then as you turned up some of the other operators, you would go into the Néel phase of the valence bond solid. I mean, that's almost the right answer. If you do numerics, that looks pretty good. But eventually, if you really look at long distance physics, long enough distances, large enough samples, it seems like there is no conformal fixed point. I think everyone seems to agree on that now.
So are there some questions from the online audience? Okay, if not, let's thanks Professor Sachdev. Let's take maybe let's take a 10 minutes break. Take a 10 minutes break and we start.
Okay. I can fix that gamma mu. Things you forget. Let's just be a gamma mu there. This is what we'll talk about next.
No, the question I was thinking was that we are not very used to this multiple carry the Berry curvature and condense.
It's a Berry phase. It's not a Berry curvature. Yeah, yeah, it's just a phase factor.
And it's condensed and filled with VPS.
Yes, yeah.
No, in this the fermion version,
The real world, the way you put a move away from the insulator is by doping the system. Now, okay, I can talk about that, but it's actually easier to first talk about just reducing the value of U or something. You just stay at half filling, or put in charge fluctuation at half filling. And that was what was done in this old paper of Asa, Demada, and Scalapino. So this is their Hamiltonian. And this is the usual hopping term written this way, where this K is the operator that hops from plus minus X and plus minus Y. And U over T is 4. And then they added this term here, which is K squared. Presumably they added this because you could still do quantum Monte Carlo without a sign problem with this term, additional term present. So of course at W equals 0, this is the usual Hubbard model with charge fluctuations, and you get the Néel state. But for W greater than 0.3, they found what could almost be a second order transition to a D-wave superconductor. Yeah, so this is one paper, and people haven't followed up. Is this a nodal D-wave superconductor, or maybe it doesn't have nodes? We don't know. It'd be great to study it and see what's happening here. So I want to now think about the possibility of this transition. Could it be second order? And can we understand this transition? And could there be some low energy description of this phase transition using the description we have developed for the insulator? So for the rest of my discussion today, I'm going to assume that if I want to describe the Néel state, I'm going to start with this theory. I'm going to start with this SU2 gauge theory with some additional dots. And so at some high energy scale, it does have these massless Dirac fermions, but eventually it confines, and these dot are chosen so that the ground state of this theory on its own is just the Néel state. So it's the world's most complicated way of describing the Néel state. But I think there's some support for this in a lot of numerical work and also some experimental work that have seen some signs of spin-on excitations. So we're going to use this theory and ask, well, can this theory undergo a transition, a different sort of confining transition, where the SU2 gauge field disappears, but instead of getting the Néel state, you get a D-wave superconductor. Okay. So now, in fact, we know the answer is yes. And again, this goes back to the very early days of ITC, where people had understood that if you took the pi flux spin liquid and in a certain gauge, and you just replace the spin-ons by the electrons, you would get the wave function of a D-wave BCS superconductor. So there were many papers on this, and the initial papers were getting S-wave, but there was a mistake. And I think Fuchen Zhang was one of those who pointed out you get a D-wave superconductor. So I want to do that in a little bit more systematic way, where I think about the gauge fluctuations more carefully and show you, how that leads to some possible second-order critical point between the Néel order and D-wave superconductor, which we've also generalized to finite doping, but let's see if I have time for that. All right, so here's the idea. So as I said, we're going to describe the Néel state by fermions coupled to an SU2 gauge field. And now I want to get rid of the gauge field because I don't want to talk about a fractionalized phase. I want to make a transition to some phase that's where there is no fractionalized excitations. Okay, now one way to get rid of fractionalization is just to have a confinement transition. And that's what happens in theory of QCD, as I've already mentioned. As QCD in 3+1 dimension, SU3 gauge field just confines, you get chiral symmetry breaking, as Nambu showed, and that gives you a theory of quarks and their masses. But there's another way to confine a gauge field, to completely get rid of it, and that's to condense a Higgs boson. And that's what happens in the Weinberg-Salam theory, where you condense a Higgs boson, which is a fundamental of SU2. And when that condenses, you get the theory of weak interactions. So that's what I'm going to do. So I want to completely get rid of the SU2 gauge field. So I'm going to condense a boson, B, which is a fundamental of SU2. Okay. Now, unlike the Weinberg-Salam model, I want to break a symmetry when the boson condenses. So this means the boson should have some other quantum numbers too, which will allow us to get, say, superconductivity. And then, so the most natural choice is to make this boson have charge E. So why would we want to make it charge E? Because if B is a fundamental of SU2, then any physical autoparameter must be SU2 gauge invariant. So if I have a fundamental B, let's give it a site label. So if we want to make a SU2 gauge invariant object, one way to make it is something like this. This is gauge invariant. But another way to make it gauge invariant is to take the following product: epsilon AB, B A of I, and B of J. You can't put it on the same site, otherwise it'll be zero. So this thing is also SU2 gauge invariant. And this has charge 2 if B had charge 1. So this is a possibility for a pairing autoparameter. And all the symmetry transformation properties of the B will tell us, is it D wave, is it S wave, what is it? And that's not something we have freedom to choose. It's just the theory will tell us what it is. Okay, so I need basically a boson to condense, and that boson must have charge E and must be a fundamental of SU2, okay? So what is that boson? Well, in fact, such a boson has been around. It's just the charge-on, I guess probably introduced first by Wen and Lee. So it has two components, B1 to B2. And it's the usual slave boson, which is the usual slave boson we're familiar with. You write it in terms of U1 gauge theory, and this is the analog for an SU2 gauge theory. So you have this number spinner of the electrons is related to the number spinner of the fermions, and this is the correspondence between them. So now you see that if I rotate psi with some left multiplied by a V, and I multiply B also by left multiplied by V, then this matrix gets right multiplied by V dagger. So in fact, you get a V dagger V here in the middle, which goes away. So this combination here is SU2 gauge invariant. And then you can also see that this boson carries charge E, because you see that this thing is charge +1, this is charge -1, and that's also correspond to this having opposite charges, because these two bosons both have the same charge. Anyway, so everything works out. This is all we need. All right. So this is the boson we have to condense, and now we have to write down some theory for the bosons to couple it to this theory. So I have to add to this action here a theory for these bosons. And now we came on this question in some complicated way recently, and this is, of course, has been done. This has all been worked out, but it wasn't for, I don't know, mysterious reasons. This is not worked out, and so we worked it out, and I'll show you what we got. So we want some effective action for the B's. And now the point is, the effective action must respect all the physical symmetries of the model and also the gauge symmetries. So here, if you look at the effective action for the F's or the psi's, that they're moving in pi flux, and also with this factor of I here. So what that means is that if I make a translation or time reversal or a rotation in lattice space, I have to accompany them with some gauge transformations of these psi's to get a Hamiltonian that has the same form, because this Hamiltonian is not explicitly invariant under time reversal symmetry or translations or rotations. It's only invariant under these operations if you combine each such operation with a gauge transformation. So the set of these gauge transformations, sometimes called the PSG, or the projective symmetry group, but really that's all it is. It's just changing gauge. All right. So, however, the C's, the original C's on the Hubbard model, they're completely insensitive to any kind of gauge transformation because they have what we'll say a trivial PSG. So therefore, you know how these transform under gauge transformation, which is they don't transform at all. You know how these transforms under gauge transformation associated with every symmetry, and that pretty much fixes the transformation of the B's. So now you know, very generally how B's must transform under all the symmetries of the problem. So we just write down the most general theory for the B's. In the antiferromagnet, the B's are gapped. So now imagine the B's are going to come lower in energy. So I just want to write down some Landau theory for the condensation of the B's in powers of the B. Okay, so when you do that to quadratic order, you get a very simple answer that the hopping of the B's has exactly the same form as the hopping for the psi's. I mean, really, that's almost obvious because any translation has to be accompanied by some gauge transformation of the psi's, and that has to cancel the gauge transformation of the B's, so the B's have essentially the same gauge transformation, or maybe the complex conjugate, but anyway. So this is the hopping of the B's. It has the same as the hopping of the psi's. The one difference is the time reversal and spin rotations are a bit different, and so this mass term for the B's is allowed, fortunately, of course. So when R is large and positive, then the theory is just this, which in the continuum limit is this, and you get the Néel state. So now we want to ask what happens when R becomes negative and B condenses. Then you go into some other phase of matter, which is going to be break some other symmetries, because ultimately the B's, and why is it going to break some other symmetries? Well, because first, the B's don't carry any spin, whereas the psi's carry spin. And also their transformation at low energies is different of the lattice symmetries. And why is it different? Well, here's the reason. So the dispersion is the same for the B's and the psi's. But for the psi's in the low energy limit, we put them over here. You half fill the band, and you put the psi here and the psi here. Okay, those are the two Dirac fermions. But for the B's, you're going to put them in the minimum of the band because there's an R that's coming up, and when the R hits the bottom of the band, the B's will condense. B's will have negative energy. So therefore, the B's are sitting here, which is a different point in momentum space from where the psi's are sitting. And that's going to make a difference to their low energy transformations under lattice operations. Another important point is that there's two of them. And why are there two of them? Well, because of pi flux. And pi flux has the property that translations in X and Y anti-commute. So the Hamiltonian for the B's has the property that translation in X and translation in Y is minus translation in Y times translation in X. And this algebra has no one-dimensional representations. So any low energy states must be at least twofold degenerate. And these are the two degeneracies here. So that's protected by the pi flux. Can't change it, no matter how many terms you add. You can increase it, and we'll do that later, but you cannot decrease it below 2. So the minimum possible, so let's consider the minimum possible thing, which seems like reasonable, at least at half filling. Okay, so you have two complex bosons, B minus and B plus. Okay, and they also have an SU2 gauge charge. All right, so that's what you have to play with. You're going to condense these bosons, and there's two of them. They have two flavors, and they have an SU2 gauge charge. So this is sounding very familiar. except the symmetry transformation is a bit different because there's a little bit different point in momentum space. This is just exactly what happened here. So I have these two bosons, which I'll call BA plus. This is the gauge index, SU2 gauge, and BA minus. All right, so I want to make gauge invariant objects of these two complex bosons. How many gauge invariant objects can I make? Well, the first trivial one is just BA plus dagger, BA plus B, well, really complex conjugate because I'm putting all the components, BA minus, BA minus. Okay, this is totally trivial. And it's invariant under all operations because it actually even appears in the Hamiltonian. That's just this term. So this obviously will not break any symmetries. It's not any operator that we're interested in. It's just present even in the Hamiltonian. So we forget about this one. But this one is present. So this is one, it's gauge invariant. So this is allowed. So that's one of them. And this is a real number. So that gives me one free parameter. Then I also have BA star plus times BA minus sum over A. So this is a complex number, so I can take its real part and I can take its imaginary part. So I have 2, and then I have 3. And then finally, I already told you what the other thing that I want. These are all charge neutral. I have the charge 2 object, which is BA plus, BA minus, B minus, epsilon AB. It's a complex number. So I have 2 of these, so that adds, well, let's say this is 1, and this is 2. And I add them up, I get 5. Is the 5 again? Well, of course it's the 5, because for the same reason, I have 8 real numbers as an SO3 gauge group, so the number of invariants is SO5. So these are the 5 autoparameters. So now all you have to do is go back, painfully go through all the symmetries, but it's really, this is a very simple exercise, much simpler than computing monopole Berry phases. And just figure out how these invariants transform under various symmetries. Okay, and when you do that, this is what you conclude. These two, I think, these two are stripes. They have CDW with wave vector pi 0 centered on the sides. This is a current carrying state. And this is a D wave. In fact, it's a D wave superconductor, not S wave, not anything else. It's D wave. So a very natural consequence of confining the SU2 gauge field in the pi flux phase is to get a D wave superconductor. I think that's a very significant fact, which has been known for a long time. Well, not in this language, but somehow, anyway, not properly exploited, in my opinion. All right, so here are the phases again. So when B condenses, these are the 2 stripe states. They have charge density waves in the X or the Y direction. This is the D wave superconductor. And this is the D density wave, as called by Laughlin et al. It has these currents flowing on the plaquettes. Yeah, so this has also been considered a lot, but although there's never been any sign of this in any experiment, we see stripes, but at different periods, and I'll say a little bit about how you get other periods in this theory. That's definitely possible. But if you took the simplest theory at half filling, you're going to get period 2 stripes. All right, so at the level of the low energy theory, over here, there's an SO5 symmetry, and all of these autoparameters have equal energy. So when you condense B, it could be any one of these 5, but they're not, of course, equal because there are other terms. There are dots, They're higher order terms that will distinguish which phase you're in. And I'm not writing them out. So this is in our recent paper. We added some higher order terms, and then you find different regions where you get a D-wave superconductor or a stripe or a D-density wave. Okay, so that depends on details that this kind of phenomenological analysis is not able to predict. So now what's the full story? When B is not condensed, we have NAIL or BBS, as I told you before. When B is condensed, you have one of these. These are total of 5 order parameters because 3 components here and 2 components here. These are also 5 order parameters. There's actually 10 different order parameters floating around, and they all appear very naturally as confining instabilities of this theory. Okay, and then as a function of R, when R is positive, B is 0, and then you're back to the old story where let's say this is NAIL, because of, and then here, when R is negative, you get one of these order parameters, and let's say it's a D-wave superconductor, and that's of course exactly the picture in the Fakir's model. So our suggestion would be that if this model, if this phase transition is second order, then there's a good chance it's this conformal field theory described by this when R is tuned to the critical point. And this theory could have an SO5 cross SO5 symmetry. There's one SO5 here, another SO5 over there. Anyway, okay. All right, so that's the basic story at half filling.
I think the key all is ABC.
Yeah.
These are first order.
Yes, 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 yeah. So that's determined by all these are higher order terms. But, you know, where the ABC is all on the right-hand side, and the NAIL VBA is all on the left-hand side. So one thing, you know, I think would be fun to study, to go back to this theory and near this critical point is measure the other, well, this is 3, this is 2, so that's 5. There's 5 other order parameters. Measure the correlations of the other 5 and see if they're enhanced near this point. Then might be you're getting close to this theory. Okay, that's the proposal. Yeah. Yes. Is there what, sorry?
Maybe I missed something. Is there any relationship between BA plus and BA minus?
Yeah, you know, they transform into each other under various lattice symmetries. Yeah, so this is in the paper. I am not showing all the details, gory details, but this B plus sits here and B minus sits here. It's just different momenta, that's all. Well, for example, if you rotate by 90 degrees, then B plus will go to some linear combination of B plus and B minus and things like that. It's in there's a big table in our paper. I mean, it's a tedious exercise in gauge transformations and symmetries on the square lattice. Things you have to do when nobody's disturbing you and keep checking it. I couldn't do it on the board, sorry. All right, okay. So now, you know, okay, I think that's I think it's a rather exciting possibility. If you want to connect spin liquids, then the most natural spin liquid is this pi flux phase, as we've argued. There's a lot of evidence for that. And this pi flux phase is a very natural connection to D-wave superconductivity. And so this, you know, this reasoning I gave you here is pretty ironclad. It doesn't depend on any particular microscopics, just depends on this very general symmetry grounds. Okay, so let's go to the real world now. This is the famous phase diagram of the cuprates. Yes. Sorry? This one? Yeah, it's just a mean field theory. So we added, what we did was we took this theory, And then we added some quartic terms. We figured out all possible quartic terms. They turned out to be 4 of them. We figured out all possible quartic terms, and then we just minimized it as a function of some quartic couplings when R goes negative. And we found exactly phases characterized by these autoparameters. Yeah.
We say from the this one, we say another kind of phase transition, such as the transition from the PDW to a valence bond order, must be in the same critical point.
Yes, yes, yes.
It must be the same.
Well, not must be. That's the proposal. That's a possibility. Yes. I mean, no, there are various terms here in the continuum limit, like quartic terms of different types and terms that couples the fermions and the bosons, psi bar, psi, b dagger, b. All of these terms have a lower symmetry. And one assumption is, the most simplest assumption is that all of these terms flow to 0 at the fixed point. Then if all of them flow to the 0 at the fixed point, you're right. Then they all must be the same at this critical point. But they may not. There may be a more complicated fixed point where some of them are non-zero. We don't know. And if some of them are non-zero, then it will not be the case that all of the different possible phase transitions in the same universality class. The simplest possibility is that they are, but we have not proven that. Yes, yes.
That paper, we read more about habit.
Not well established.
Yeah, not very established.
So what are your basis of that? I mean, there's only one paper, I agree.
Say that is the way. So they only see some signature of the
Okay, yeah, well, fine. No, I agree. You know, there's only one paper, and I would love to see more studies of this model. Yeah, absolutely.
So we also try to propose a model we have direct connection from this near order to a node level. And finally, we always get a resistance.
So what model was that? Sorry?
We try to design some model.
Yes.
Rotor cover the function.
Yes.
To make that rotor have to use. Then we always find the resistance is near order and gap in the.
Yeah, well, but you know, I don't want to do rotors and say I want electrons. The model of electrons, it should have only electrons. That's the nice thing for this.
I didn't find any.
Okay, all right. Okay, I mean, maybe we need some other model, but I think the reasoning is very general, and yeah, it'd be great if you can find some model. I'd like to find a model with only electrons, no rotors and stuff like that. Yeah.
For the system to have like single conductor?
Not in terms of a second order transition from a pi flux phase. You start from the pi flux phase, and then you just Higgs out the gauge field, and then the only superconductor you will get is a D-wave superconductor. There could be other spin liquids, different spin liquids that'll give you other things. But this one only gives you a D-wave superconductor. Yeah, the fact that this changes sign under 90-degree rotations comes from the PSG of the original spin liquid. Yeah. I mean, that's in fact the name of the game. In fact, even the whole VBS thing, you know, you have some confinement, and then the structure of the previous spin liquid tells you what the confining phases are. It restricts the confining phases. That's what I've been everything, all these 10 phases are different possibilities from confining the pi flux phase. And it's just these 10, nothing else. Yeah.
Probably has the marking the SO5 in each time.
Well, I mean, the only place there's an exact SO5 symmetry is if there is a conformal fixed point. Now, at least at the level of field theory, this is very likely, this field theory as written down, almost certainly has a conformal fixed point. Because this, without the bosons, it was almost conformal. Now I added 2 more massless bosons. That should be enough to put it over the edge and make it conformal. Okay, so this field theory, absolutely, I'm very confident has a conformal fixed point with SO5 plus SO5 symmetry. That's a different question, whether the original lattice model, which does not have, this field theory has explicit SO5 cross SO5 symmetry. Every term in this theory has explicitly SO5 cross. If I forget the dot, 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 this field theory has explicit SO5 cross SO5 symmetry. So, lattice gauge theories could just simulate this. But our lattice theory does not have explicit SO5 plus SO5 symmetry. Once you put it on the lattice, when you take this theory plus some high order term, this does not have SO5 plus SO5 symmetry. It has SO3 for spins, it has U1 for charge, and it has Z4 for lattice rotations and things like that. All of those symmetries are not, those are exact, but that's it. Will that theory have an SO5? I don't know. Okay, that's really the question. Yeah. Yeah. I mean, the boson theory, of course, can be trivially gapped, because when you take this boson theory and you make R positive, then the bosons are just trivially gapped. But the fermions are there, and the fermions have an anomaly. The fermionic theory it cannot be trivially gapped. Yes, and it's again the Lieb-Schultz-Mattis anomaly essentially. It's this Wessumino-Witten term there. Yeah. But there's another, I'm not sure, I'm not enough of a anomaly person to really say this. There's another, I think maybe the question you're asking, suppose the boson is condensed. Can that condensed boson phase, the Higgs phase, be trivial? And the answer is no, because simply because I couldn't find anything. That's the only way I know to prove it. It's either a superconductor or it breaks translational symmetry. So there's some U1 cross translations, and one of the two has to break when B is condensed. I think it's ultimately tried to Tx equals minus Dy. That's enough to imply that. Okay. I'm sure you're all pretty tired. So what about the real world? Okay, so let me just actually summarize by saying that there's some, this is the famous phase diagram. You've probably all seen this before. But there's some really big puzzles about this phase diagram, which I believe that this theory can help solve. So what are the puzzles? So one puzzle you can already see here. So of course, it's a D-wave superconductor at 0 field. But when you apply a magnetic field, you get charge order, or you get charge order correlations in this region, and with fluctuations. And what you see here, very evident, that the TC for charge order and the TC for superconductivity are pretty much the same. Why should these things be the same? If you had a Fermi liquid theory and you were doing instability to charge order or superconductivity, you'll get completely different temperatures, completely different energy scales, because they depend on very different interactions. For some reason, they're almost the same. Okay, and that's why this is exciting, because here, if you had this SO5 symmetry, charge order, stripes, and superconductivity are the same. They're part of the same SO5 multiplet. Okay, so that's one of the motivations for doing this. That's got me excited. You're getting stripes here, so it helps, at least points towards one of the striking features here, that the temperatures of CDW and superconductivity are the same. And this really could do that. Okay, that's one. What's other things you see? So then you, of course, if you look here at higher temperatures, you have the pseudogap, and there's gaps over here, very different from the Fermi liquid spectrum here. So you need a theory for something that has these pockets, but with no broken symmetries here. Nothing, the charge order or any kind of superconducting fluctuations, you don't see where you see this spectrum at much higher temperatures. The pseudogap clearly develops. So what is this state? So I believe this is a state which violates the Luttinger theorem, has an underlying spin liquid, which I would like, now I believe it's the pi flux spin liquid. Okay, so that's another reason for thinking about this system as the instability of not a Fermi liquid, but the instability of a pseudogap, which has an underlying spin liquid. And finally, another major puzzle are these quantum oscillations. So you've seen quantum oscillations in YBCO appear at high fields, as discovered originally by Louis Taillefer. And these quantum oscillations have been interpreted in terms of some electron pockets that are induced by charge density waves. That seems to be the reasonable solution. But if you go in and do a model, suppose you imagine you had a Fermi liquid as your parent state, and you put a charge density wave on top of it, and then you try to match the quantum oscillations. You find it fails completely. In particular, it tells you that there are some Fermi surfaces in the nodal regions, in the antinodal region, which never been seen in quantum oscillations, or specific heat measurements and so on. So it's also very clear that this charge-ordered state and the quantum oscillation do not appear out of a Fermi liquid. They do not appear instabilities out of a Fermi liquid. So I would say there's, just tremendous evidence that if I come down in this direction and lower the temperature in the cuprates, the normal state cannot be viewed as a Fermi liquid. And the theory of charge density wave order and superconductivity that you learn in your courses, how they appear from a Fermi liquid, completely fails to describe what's seen. Okay. So we want some other normal state, and then we want to, now that normal state, should have this rather anomalous Fermi surface. And again, by some anomaly theorem, that implies there must be some spin liquid there. So the normal state should be some spin liquid plus Fermi pockets, and then that undergoes a confinement transition, which gives you what you see at low temperatures. Okay. Yeah, to me, these seem now, pretty reasonable hypotheses, although I wouldn't say everyone, and most people probably disagree with me, but hopefully I've convinced you. What else could it be? Okay. All right, so then there's a lot of things to do here. One is to describe this this state over here. And yes. I know. Pair hopping term? What pair hopping? I didn't put any pair hop. Oh, the case. That was just, okay. In fact, we did the whole theory without even knowing about that paper. That's just a nice way to motivate it. Okay, go ahead. Yeah. I know.
What's the difference between the separation half free and the separation away from half free?
That's exactly what I'm trying to do.
Okay.
Yes, that's what 15 minutes? Okay. All right, so let me just give you an outline of how this works. So normally, when, in the old days, when people started doping, what did they say? If you open up the reviews of modern physics of Wen and Lee and Nagosa, they write this down, and they go away from half filling, and that tell us, they say that means that these bosons have density equals P. The density of the charge goes into these bosons, like you also did in your presentation. These bosons have a charge density. Okay, so step one is that we don't believe that's what happens. And the clearest way to see this is in terms of the ancilla theory, but it was actually also mentioned by Wen and Lee in one of their papers. So you're putting these, you're putting some charge in. Now the charge can go into the bosons, but can also go into bound states of the bosons and the Fermi. It can go into the electrons. So the idea is that the pseudogap has two components. It has one component, which is electrons, which carries the charge. And these electrons form little pockets over here. And the spin liquid remains a spin liquid. It's exactly the same spin liquid with, on top of it, some charge carried by the bound states of the spin-ons and the charge-ons. So basically, the spin-ons and holons form a bound state. That takes up the charge. And then, so those are sitting there. And then you have a theory of the spin liquid, which is still the same spin liquid. Nothing has changed. I mean, it's coupled to the bound states, but the zeroth order is the same spin liquid. So if you accept that, now we can do a microscopic theory of that. That's where the ancilla model of Yaori Zhang comes in. Well, okay, but let's accept that for now. So to tie that together with the rest of my lecture, then basically I have to look at the same spin liquid theory to zeroth order, even at finite doping. So what I'm going to assume, oops, okay, yeah, no, I don't have this here. So if I had this dispersion for the bosons, which looks like this. There were these two Dirac nodes, and then there was one minimum here, another minimum there, something like that. This is B plus, and this is B minus. Okay. So now if I dope, I'm going to get additional terms in my boson Hamiltonian. I had only nearest neighbor terms, but now you can ask, what about second neighbor terms and third neighbor terms? Again, those are heavily restricted by the symmetry transformations. So you work those out, and you find that you can get the situation where this thing has a double minimum. Looks like this. So now there's 4 bosons here that can condense. And now you can do the same symmetry analysis to figure out what are the possibilities. So that much we have done. It's still quite complicated, but that much we've done, and you get all kinds of possibilities. And you can get, period 4 stripes, for example. Okay. And you can also get a pure D-wave superconductor. In fact, these 4 things gives you a pure D-wave superconductor with no broken. Huh? You must what? Yeah. This comes from the second neighbor hopping, third neighbor hopping. I mean, the possibilities are very large, but this is just a method. In principle, we can show you can get a period 4 stripe. You can get an ordinary D-wave superconductor, even with this double minimum. It's still a D-wave, pure D-wave superconductor. You could also get pair density waves. So possibilities become very vast, unfortunately, but they're not infinite. And they include what's seen. Okay. So this is a relatively minor modification of our theory. Okay. All right, so this is kind of the picture that you have this pseudogap, which is what we call FL star. And think about this FL star as a superposition of 2 different things. One is that the spin-on and holons combine to form a Fermi pocket, and then there's a pi flux spin liquid. So let me say a few more words about why this is very reasonable. And the usual slave boson theory really is a bit unphysical. And the reason is the following. So when we write down the TJ model, as you did in your lecture, you have some T term, which is B dagger I, Bj, F dagger J, Fi. And then you have a J term, which is F dagger I, J, I, something like that, F dagger J, F, J, with some sigmas here, something like that, okay? So the picture is that because of the J, the spin-ons deconfine. But there's a T term here. And this T term, this term, is like an attractive interaction between the B and the F. So if I have a B moving around and there's an F moving around, there's an interaction between them that's T, which is attractive. And now T is much bigger than J. So in the TJ model where T is much bigger than J, spin-on and holons will always bind because this is a very strong attraction. So in fact, spin-ons, all the holons will bind a F to form an electron. Okay, these electrons, that will give you the whole pocket. So there'll be bound states of the spin-on and holon, give you a whole pocket. But the remaining spin-ons are still left. And in fact, the PhD restricts their dispersion. They can't change. And so the ancilla theory gives you a way of describing this physics in a very systematic way. The usual theory of the TJ model, where this is really valid when J is much bigger than T. Then you can use it. But in the real world, T is much bigger than J. Okay. Yeah, all right. So this is like our picture. This is the mother state, or as Patrick said when he saw this picture, I call it the parent. It's the parent state. It's just this, basically a pi flux spin liquid and small Fermi surfaces. Now, if you condense, if you go along B, you just condense Z alpha and some, because this pi flux is dual to CP1, you can condense Z alpha and that gives you the Néel state. Then what I have described is this, where you condense this capital B on the pi flux spin liquid, and I've described in the simplest case with only 2 minima, but you can get multiple minima, and then you have all kinds of phases. And finally, there's a transition from here to the Fermi liquid, which I have not said anything about. That's quite a different theory, and the only way I know how to do that is using the ancilla theory. That gives you some kind of possible strange metal in between. Okay. Maybe tomorrow I'll say a little bit about this. So, all right. I think I don't have that much time. I mean, I could, well, we'll see. I can't explain the ancilla theory in 5 minutes. Okay, I can try. But before why don't I try it? And then we can have questions. Okay, so a lightning review of the ancilla theory. Okay, so what is the ancilla theory? Well, it's just a way of describing the Hubbard model in a different way. So suppose I start with the Hubbard model. I have a system here of electrons on some, this is a square lattice. I'm just looking at it on edge, but you can do this in 1 dimension too. This is a square lattice with some Hubbard repulsion U, okay? Now I'm going to derive the Hubbard model in a different way. I'm going to take free electrons and couple them to a bilayer antiferromagnet. Okay, so this is these are spins now. There's a bilayer antiferromagnet. Exactly at, each layer is at half filling. And there's a coupling here, J perp. There's a coupling here called J condo. Okay, now let's imagine that we are in the regime that J perp is much, much bigger than J condo. Then what's going to happen is that these spins are going to form singlets, and that's just going to be the ground state. All right. All right, so now let's look at the effect of JK. So what JK is going to do is going to couple the electron here, if it happens to be there, to this electron, and that's going to excite this to a triplet, which has an energy J perp, and then it's going to come back. Now that process, like any process in second order perturbation theory, is going to lower its energy. So what this tells you is that the consequence of JK, if the site is singly occupied, its energy will go down. Okay, and how much will it go down? will go down by jk squared over j perp, second order perturbation theory. So you just work it out in great detail. I mean, if you have, you'll find there's a Hubbard repulsion, which is jk squared over j perp. So this model, in the limit this is true, is just the Hubbard model, where u is jk squared over j perp. All right, to check that. So all I've done is rewrite the Hubbard model, that's all, in this limit. Of course, now what I'm going to say, I'm going to drop this limit and analyze the model more generally. So that's the uncontrolled part. But now if JK is if this is true, then this is, kind of very simple. These spins disappeared and they form singlets, and this forms a Fermi liquid. So if I look at this model as a function of j perp over jk, then certainly for large region, it's just a Fermi liquid because it is almost free electrons. Okay, but let's imagine there's something else. Under renormalization, you do some RG, jk becomes large. Now, why would jk want to become large? Well, because this is the Kondo coupling of spin to conduction electrons. And we know Kondo coupling flows to infinity. So let's imagine there's some renormalization and jk has become large. So when jk has become large, what happens? Well, now we have a very different picture. So when jk has become large, what's going to happen is these spins. So we forget about j perp and imagine jk is large. These are spins here. And there's also spins over here. But let's imagine we're in some limit over here, but this is very large, and we can forget about this. So if you forget about this, this is just a Kondo lattice. What does a Kondo lattice do? The Kondo lattice will form a heavy Fermi liquid state. What's the size of the Fermi surface? The number of holes here is 1 plus p. The number of holes here is 1. So the size of there's a large Fermi surface of size 2 plus p. But 2 plus p is the same as p mod 2. So in fact, it's a small Fermi surface. So this gives you the whole pocket. And what do these spins do? Well, they're my favorite pi flux spin liquid. So this gives you a very explicit way of getting a phase which is like the pseudogap, where you have a small hole pocket and you have pi flux spin liquid. And that is a possible ground state, at least of this tri-layer system. Whether it's actual ground state of the Hubbard model, I don't know, but I think it's a good possibility, at least at these temperatures. Okay, I'll stop there.
Yeah, we have quite some time to ask questions. Yeah.
Yes, it requires 3. Yeah, so in fact, the point is you can, if you're given any system, you can always add a bilayer to it because the bilayer has a trivial ground state. So it doesn't change any of the anomalies or Luttinger count or anything. You cannot add 1 layer. You can add 2, 4, 6, 8. So smallest is 2. And that doesn't change the underlying Luttinger rules and so on. And that's very nice because you see when you get a small Fermi surface, if you just added 2 layers, you added 1 layer, you get a Fermi surface of size p. That contradicts the Luttinger theorem. But if you have a spin liquid, then we know that the anomaly of the spin liquid can account for the full Luttinger count. Yeah. So that's why you need it has to be there. And in fact, it's this spin liquid that's describing, in the end, the onset of superconductivity. If you didn't have the spin liquid, you wouldn't even get the superconductivity of the charge order. It's really important. Mm-hmm. So there's a lot of work on hole pockets with strange things called Green's function zeros and DMFT. Mm-hmm. There's infinite number of papers. There's the YRZ model. All of those don't have the spin liquid. So that's some way of getting almost the same physics as in some DMFT approximation, which completely ignores these anomalies. So yeah, I mean, it's useful, but ultimately it's not correct. Sorry, it's being recorded. I'm going to be attacked by, there's a huge amount of work on that. Yes. No, it's fine. It's very good. It's just,
don't worry. It's mainly to the
people have something called Luttinger surfaces and all that. So I would say the Luttinger surface is the best approximation of DMFT to a spin liquid. But if you want a real theory, you have to deal with it honestly with the spin liquid.
What has the second layer of the scalar is a pi plus the spin liquid? Do you need to add some interaction in the second layer?
Well, just an assumption. Yeah, of course. I don't know what it is. I'm just going by the, I want, the whole lecture is about just looking at the data, looking at the numerics, and that's guiding me to what's the best possibility here. Yeah. Of course, we would love to do some microscopic calculations. I think Hui and has some variational Monte Carlo recently, and also several other people, including my student Henry, are working on that right now. And so those kind of questions would require some more serious numerical analysis of this model. Yeah, people are working on it. Yeah. Yeah, you can certainly add lots of interactions, but I think most of the work right now is the level of variational wave function. You just take a wave function on 3 layers and you play with it and see what it predicts. So you can take the 3-layer model and write down a wave function for this physical layer. It's sort of analogous to the Gutzwiller projection. You take the wave function, which has 4 states per site, which is just free fermions, and then you project onto 3 states per site, and you get a Gutzwiller projected wave function for the Fermi liquid. Here you have, 4 times 2 times 2, 16 states per site, and you project out all of these 4 states here, and you get some wave function for the physical 4 states. That's an approach that many people are taking right now. Yeah.
Yeah, I actually have a question about the part you make the connection to the real world.
Yes.
So the part I'm not very sure was that you say the onset temperature of the charge order and the superconductivity are similar.
Similar, yes.
Yeah, and the argument was that they are all the SO5 multiplet. They are all that's one. That's a proposal. So but if one take this seriously, like literally, your field theory it's at 2+1.
Yeah.
If you break this SO5.
It's not exact, of course, and the TCs are not the same either. But it's a theory where the first term, the first term being just this hopping term, which is the most important term, makes them equal. Then there's a lot of effects that make them different. But the first most important term has them equal. Yeah, that's all. That's all I'm saying. Whereas in Fermi liquid theory, it's not like that at all. Every term is different. Not even the first term. One is some particle-hole susceptibility, other the particle-particle susceptibility. There's no reason for that to be the same. Yeah, they can be exponentially different.
Okay, so Xiaoxue, are there questions online? Okay, I think good. If not, let's really thank Professor Sarstedt. Yeah. So that's for today. So tomorrow morning, I think 10:30, right? We will have a talk by Dr. Junchen Rong on the introduction of CFT. So please still come here. Also for the online audience, tomorrow morning 10:30, and tomorrow afternoon is 4:30, right? Still 4:30. So Professor Sarstedt will give the 3rd lecture on the strange metal, SYK. Yeah. Okay. Yeah. So see you tomorrow. Yes. Yeah.